Assalamualaikum warahmatullahi wabarakatuh. My name is Ali Faiman bin Azhar from Group 7. Now I want to present to you SCL1 Electrical Circuit. So basically here is my team members: Dayana Amalia binti Kamaruzaman, Shasha Shazwani binti Razali, Umi Hafiza binti Muhammad Rahim, Aurora Tristi Analakal, Ali Faiman bin Azhar, Jamshid Ani bin Jamal, and Muhammad Hakib Hakimi bin Aslan. The question that we get is electrical circuit is RC circuit. Study the charging of a capacitor in an RC circuit. The question is dV over dt equal to 1 over RC, V source minus V, where R is resistance, C is capacitance, and V source is the source voltage. The goal is to solve the ODE using numerical methods to find the voltage across the capacitor over time. Real-life application: analyze the behavior of electrical circuit. Introduction. Resistor-capacitor circuits are essential in electrical engineering, used to study capacitor charging and discharging behavior. The governing equation for the voltage across a capacitor is dV over dt equal to 1 over RC V source minus V, where R is resistance, C is capacitance, and V source is the source voltage. This objective is solve this ODE numerically and analyze the voltage behavior over time. The method that we use is first one is fourth order Runge-Kutta method (RK4), accurate and widely used single step method. The second one is Adam-Bashford method, explicit multi-step method that leverages prior values and efficiency. The last one is Adam-Moulton method, implicit multi-step method that improves accuracy by using future value. Results are compared to the exact solution. V exact t equal to V source times 1 minus exponential time to the power of negative t over RC. Another one is to evaluate the accuracy and efficiency of each method. So my group has chosen the Adam-Moulton fourth-order method. First, we start with the parameter, resistance, capacitance, time constant, source voltage, initial capacitor voltage, time step, and total times. The formula is dV over dt equal to 1 over RC V source minus VC equal to 10,000 times 10 minus VC. So for the first step is Euler method. By using its formula, we can get the iteration 1. When we can get the iteration 1 by get the 10 volt, then we can get the iteration 2, which is it will give us the 10 volt 2. Then we can see the formula at the right side is VCT plus delta T equal to VCT time plus delta T over 2 FT VCT plus FT plus delta T V predict. The predictor by using the Euler method is V predict equal to VCT plus delta T times FT VCT. The character for Adam-Moulton is VCT plus delta T equal to VCT plus delta T over 2 times FT VCT plus FT plus delta T V predict. Iteration 1. T equal to 0 becomes 0.0001. The first one is initial value VC0 equal to 0. Predictor step, V predict C 0.0001 VC0 plus delta T times F0 VC0. V predict 0.0001 equal to 0 plus 0.001 times 10,000 times 10 minus 0 equal to 10 volt. The character step, VC 0.0001 equal to VC0 plus delta T over 2 F0 VC0 plus F 0.0001 volt predict 0.0001 VC 0.0001 equal to 0 plus 0.0001 divided by 2 times 10,000 times 10 minus 0 plus 10,000 times 10 minus 10. VC 0.0001 equal to 0 plus 0.0001 divided by 2, 10,000 plus 0 equal to 5 volt. The iteration 2 is T equal to 0.0001 becomes 0.0002. The initial value is VC 0.0001 equal to 5. Predictor step, V predict C 0.0002 equal to VC 0.001 plus delta T F times F 0.0001 VC 0.001. V predict 0.0002 equal to 5 plus 0.0001 times 10,000 times 10 minus 5 equal to 10 volt. The correct step is VC 0.0002 equal to VC 0.0001 plus delta T over 2 times F 0.0001 VC 0.0001 plus F 0.0002 V predict 0.0002 VC 0.0002 equal to 5 plus 0.0001 over 2 times 10,000 times 10 minus 5 plus 10,000 10 minus 10. VC 0.002 equal to 5 plus 0.0001 over 2 times 50,000 plus 0 equal to 7.5 volt.
Thank you, Aiman. For algorithm, first we initialize the parameter. This parameter we can include the R equal to 100 ohms. The capacitor is 0.00001 farads. The voltage source is 10V and the initial capacitor voltage is 0V. The time step we use is delta T equal to 0.001 seconds. Then we calculate the time constants T equal to RC is 0.001 seconds. Then we set the time, simulation time is S equal to 10 seconds. Second step, we define the governing equations. Use the different equations for the capacitor voltage. And then we represent the equation for the function F in bracket T, comma V in bracket equal to 1 RC in bracket V source minus the V capacitor. For step 3, we implement the fourth order of Runge methods for each time steps. We predicted the step which we use the Euler methods for V predicts equal to V plus T F V comma T. The correction steps we use the alpha methods to find the V new equal to V T2 in bracket F T comma V plus F in bracket T plus T over V predicts. And then for step 4, we calculate the exact solutions and compute the exact solution each time we using the formula. For step 5, now we compute the calculation error at each times. And then for step 6, we tabulate and visualize the results. We create a table following the columns times numerical, exact solutions and the error. We plot the graph, use the MATLAB. We first plot the numerical versus exact solution and error over the times. For step 7, we verify the result and compare the numerical and the exact solution to ensure the error decreases as the time step is reduced. This is programming for MATLAB codings we use. First, we input the parameters in the codings and then we use the formula to find the equations. For second part of the coding, after we use the Euler equation, we find the other multiple methods and then to find the V predicts and V corrector for these equations. Then we compute the error in these codings. After we put all the coding together and run it, we can get this graph. What is this graph show? The error analysis. First graph show the capacitor voltage, which is analytical versus numerical in Adam Mountain, and second graph see the error analytical Adam Mountain methods. The difference between the Adam Mountain methods and the analytical solution for the RC circuit arise due to the following factor. First one is numerical approximation in Adam method. The Adam method is the numerical approach which use a predictor and corrector schemes to approximate the solution and different equations. The predictor steps we use Euler method introduce some initial error, and although the corrector step we find it, the small discrepancy still remains. Second one, the factor is the time steps. The time step is delta t. In the numerical methods, the time steps delta t play a critical role. While the smaller delta t reduce the error, it cannot eliminate it entirely. Because of that, they have the difference between the analytical and the numerical method we use.
Okay, now I want to explain about the graph, where the graph is about RC circuit simulation using Adam-Moulton method. So I want to highlight 4 key points from this graph. So the first one is about curve characteristic, where the voltage starts at 0 voltage and rises to 10 volt following the exponential charging behavior of an RC circuit. And then it rapid rise in voltage occurs for t less than 0.002 second, followed by a steady state at 10 volt. The next key point that I want to highlight about transition phase, where steep increase correspond to the capacitor's charging phase. And the next one is about steady state, where after t approximately 0.002 second, the capacitor is fully charged with no significant current flow. And the last one, Adam-Moulton method, it shows that smooth curve indicates the method accurately, the charging process, and it's suitable for solving the exponential dynamics of the RC circuit. Okay, next, I want to explain about the advantages and limitation of using Adam-Moulton method. So the first one, the advantages is fourth order accuracy, where it provides higher accuracy compared to many explicit methods, and it also improves stability, effective for stiff equation for larger time steps without stability. And the last one is it's suitable for problems where explicit methods require in practically small step size. And there's some limitation of using this method. First one is about implicit nature, where it requires solving a system of equation at each step, increasing computationally cost and complexity. The next one is initial values requirement, where it needs initial values from previous steps, often obtained using another method like RK4. And the last one is computational effort, where while offering better stability, it is less efficient than explicit methods for non-stiff problems due to additional computational effort. Okay, next, I want to explain about the real-life application of the problem. So the first one is orbital mechanics, where it used for accurate and stable solution over long periods. It also used at astrophysics when employed in simulating planetary motion. It also will be used in satellite orbits. It's applied in the long-term dynamics of satellite orbits. And the last one is also can be used in handling stiff equation, were critical for maintaining stability in these applications. Okay, let's move to the conclusion part, where we can conclude that each of these methods, Runge-Kutta fourth order, Adam-Bashford, and Adam-Moulton, offer distinct advantages and limitations. While Runge-Kutta fourth order is highly accurate and suitable for many general purpose problems, the Adam-Bashford method is more computationally efficient for certain systems but may face stability issues. On the other hand, the Adams-Moulton method provides greater stability, particularly for steep problems at the cost of higher computational demand. The choice of method depends on the nature of the differential equations being solved, the desired accuracy, and the computational resources available. Alright, I think that's all from us, Group 7. Thank you.